Hello everyone, myself Chong Sinzum Lachumpa. So today I'm going to talk on the topic the use of collimator to restrict the radiation dose. So before discussing, I want to talk on this topic, the collimator. A collimator is a device that shapes and directs radiation beams like X-rays or gamma rays. And how does it work? It uses metal blocks or leaves to control the beam size and shape, allowing precise targeting of tumors or areas of interest. So it proposes our number one, accurate targeting, which delivers radiation precisely to tumors. And number two, minimize the damage, which protects surroundings and of healthy tissues. So common applications are number one, radiation therapy for cancer treatment, and number two, medical imaging, which improves image quality. Now I'm going to share the research paper. So recently, we reported on high degree of consistency between the drive-by response of a slot collimator to a point-wide radiation source and a sink or slamping functions as per the Lipase transform of a unit impulse, extending this idea to more complex field geometries. One approach is to use collimator materials that are not homogeneous. This approach offers potential of producing graded shielding solutions, but very importantly, they are also attractive because of their low mass payload, making them valuable alternatives to conventional high density collimators. So in this, I would like to explain is like the main problem is like the radiation detectors and the necessary shields called collimators that focuses the radiation are traditionally made of very dense or heavy materials like solid metals. So this weight is a huge issue for robots, drones and underwater vehicles that needed to carry them. So limiting their flight time, battery life and the moment of data they can accurately correct. So the proposed solution that I want to share is the paper process or novel, lightweight system that uses low density shielding collimation materials like special metal forms or composites instead of solid heavy blocks of metals. So this lightweight shielding will be integrated with low power electronics. So now I would like to share the book chapter. So the topic is the calibration of MLC leaf positions. An important procedure to ensure accurate leaf positioning is the calibration of leaf positions. Through the calibration, the major signals such as voltage from the pentitometers or pixel numbers from a solid state camera and actual leaf positions establish a one-to-one relationship. Periodic checking and recalibrations are also needed to ensure the integrity of the controlling system. So I would like to say that the importance of calibrations. Calibration ensures accurate leaf positioning by establishing a one-to-one relationship between major signals like voltage from pixel numbers from a camera. So another I would like to talk is the variant MLC calibration method, which uses narrow infrared beams in the collimator assembly to calibrate leaf positions automatically with when the MLC operating system initials. Each leaf position encoder values are acquired as it interacts the infrared beam and are used with equation tree for calibration. So this is all I want to say on this book chapter. So now I would like to show you lab video. Hello everyone. So today I'm in radiology lab. So today I'm going to demonstrate the collimator. So first of all, I want to talk about collimator. Collimator is a part of X-ray machine, and it is a device which controls the shape, size, and the radiation beam. So this is the collimator. So you can see here, this is the adjustable metal shutter which helps to open and close the beam of the projection. So I'm going to show how to use the collimator. So I'm going to turn off the light because the collimator is not visible. So this is how we adjust the collimator with the help of shutter. So to expose the area we needed. Thank you. That's all I want to share about the collimator. Now I would like to share the case study video.
All right. Today we're going to be talking about collimation of your X-ray beam. So how does the actual collimator work? What's the reason for doing collimation in your X-ray beam? Coming up right now at How Radiology Works. This is our X-ray tube right here. And then we have X-rays coming out, divergent manner, right? So X-rays are coming out all throughout here. And then we have a housing actually around the tube itself. And the idea is that, for instance, the size of our image receptor is limited. So we have an image receptor that's here. If we had radiation that was going all throughout these areas over here, there's actually no way that this would actually even land on the image receptor. That's the first reason why we want collimation. And then the second reason is if we're interested in our anatomy that's on the image receptor, which is only in a given smaller region. If the anatomy we know is going to land within a smaller region on our image receptor, then this radiation right out here, this is actually wasted radiation as well. What we're defining today is actually to bring in just metal from the side such that we can essentially block the radiation, and we'll have the metal coming in from this way and the metal coming in from this way. And the idea is it will block the radiation so that it will get absorbed primarily with metal region. So we call that the collimator. So after we bring the collimator in, then we're limited actually to radiation only within what we call the field of view that we're prescribing. So the region of radiation which we would like to irradiate will have the primary radiation, and there will not be radiation out here in the region where we're blocking it primarily with these collimators. So the collimator is defined actually in a plane that's relatively close to the tube. And then what we often care about is we have a patient that's right in here, lying on a table. We could talk about this here being the field of view in terms of the collimation. I'm only drawing a picture here in 2 dimensions. This is a 3-dimensional case. So we actually have collimators coming this way, and then also collimators coming in and out of the board. On our figure, you have the X-ray source, and then you have the beam, which is actually collimated down by the collimators here on the side. We'll define a field of view in the object plane of the patient. Then you can see the field of view in the patient plane here. And then you can also see how that's defined on the detector, where in this case, we've only combed down a little bit, so most of the detector is actually covered. Then in order to visualize this,
So in this video, what I would like to say is as about the collimator. So how does it works, or how does the collimators demonstrate while radiation exposure? So it uses the metal blocks that you have already seen in the video, which leaves control the beam size, shape, and allowing precise targeting of tumors areas of interest. areas of interest, and it uses so it uses accurate targeting, deliver radiation precisely to tumors, and number two, it minimizes the damage, protects the surrounding healthy tissues. So this is all I want to say on this video. Thank you.